Hi, I'm Dr. Angela Stickle, a lunar and planetary scientist at the Johns Hopkins Applied Physics Laboratory, and also the Autonomous Systems and Robotics Systems Integration Lead for the Lunar Surface Innovation Consortium.
And I'm Dr. Benjamin Greenhagen, a planetary scientist here at APL and the Assistant Group Supervisor of the Moon and Rocky Planets Group. Let us consider the Moon's illumination. The orbital period of the Moon around the Earth is 27.3 days. During this period, both the Moon and the Earth are changing their positions with respect to the Sun. As a result, sunlight takes over 2 additional days to hit the Moon in the same way that it did on day 0 of its orbital period. This is the reason why it takes 29 days to observe a full lunar cycle, which has 8 phases that describe how the sunlight hits the Moon.
As the Moon moves through its cycle, it is illuminated for approximately 354 hours, followed by approximately 354 hours of continuous darkness. But at the poles, the situation is a lot more complex and extreme because of the axial tilt of the Moon relative to the solar ecliptic. As illustrated in this image of the lunar poles, the average illumination map exhibits fractions of permanently shadowed regions and a few locations that enjoy near continuous sunlight. Illumination is perpetually at grazing angles because the Sun is never more than 1.5 degrees above or below the horizon. With the Sun at such a low angle, the local terrain affects the resulting illumination pattern.
An extreme example are the floors of deep craters, always devoid of sunlight. Places that sunlight never reaches are known as permanently shadowed regions. These extremely cold locations can trap volatiles, including water and hydroxyl, species that would otherwise immediately sublimate in the harsh, airless sunshine that illuminates most other places on the Moon. Overall, the resulting illumination pattern is truly unlike anywhere else on the Moon, or on Earth.
Let's take a closer look at these polar regions and how variable they are. On the top right, you can see a video of a region that is close to the Moon's south pole, and how the lighting conditions in this area change as a function of the sun direction. If you look at the changing conditions and the time frame of these, you can see that you are subjected to long periods of direct solar illumination and long periods without it. Similarly, on the bottom right, you can see the Whipple crater, which is a North Pole crater, and the illumination conditions at the same local time during the northern summer, equinox, and northern hemisphere winter.
These highly variable polar lighting conditions depend on the season, location, and local topography. As the sunlight traverses the surface, changes in temperature occur quite rapidly, going from very hot to cryogenic in a shock-like fashion. As such, illumination also poses a challenge to thermal management and modeling for lunar surface and hardware. Without a diffusing atmosphere, shadows are very stark, leading to significant difficulties in the use of visual systems that can determine terrain and distances. This results in challenging landing site modeling and mapping for local assets.
As you design your hardware and landing site, you should consider the target illumination environment and how it is modified over time, both by the natural sunlight patterns on the surface and any shadowing effects posed by the actual system. And whether the systems are meant to stay in place or be mobile assets, it will be critical to consider how illumination affects their function and performance. Power sources, such as solar panels, will need to be engineered to account for their position. You may need to play with the solar array geometry and height to overcome any changes in local illumination. A mix of power generation and storage technologies should be considered for those instances in which there is significant lack of sunlight, such as the lunar night.
For mobile assets, as you traverse the lunar surface, you will want to chase the light and position outposts in beneficial locations, such as those highlighted in the image on the right of the Shackleton crater rim. If you can move between these stations, you can remain in sunlight continuously. In the absence of sunlight, consider other illumination sources, such as earthshine and starlight. While not useful for power generation, a lot of reflected light can still enable visible imaging and navigation.